today's lesson is there's not a whole lot of math. I don't know if it's the bad part of the lesson. The bad part of the lesson is there's just a little bit of information. Most of it's common sense, though, if there is such a thing. So if we want to just study reaction rate, we can do that mathematically, and we did that already. And basically, if I want to look at reaction rate, the rate of the collisions between reactants, so that's going to be important. For the reactants to make products, they have to hit each other and make the substance that is produced. I mean, they have to touch each other for the atoms to rearrange. Also, we have to look at the percentage of collisions that are oriented the right way. And so I have an activity for you that will help you. And then the percentage of collisions with enough energy to actually produce a reaction. And I have marbles for all these things, so don't freak out. So let's do this first. The collision rate. As the concentration of reactants and the liquid or gas phase increase. Yeah. Okay, I'm going to pause the movie and we're going to play. Alright, so we just saw that as the concentrations, so the more products or more reactants you actually put in the reaction, you're going to get more reactants out. If you increase the surface area, usually that's by grinding it up into a fine powder. That's usually how it's like worded. I've seen that actually like in words. And then if you increase the temperature, you're not only going to increase how fast they're moving around, but the energy that goes into the collision will be greater as well. So not every collision is going to make a chemical reaction occur. So with your marbles, I gave you two oppositely sides of Velcro. I don't know how to say that. But like if I took two smooth sides and I went like this, make a product, I said, like that would not work. So you have to have correct collision orientation. And then you can make a product. See? That's okay. So up here in a little bit more complicated example, if I have this NO2Cl and then I have some nitrogen dioxide, oh excuse me, my bad. If I have
two molecules.
I was like, what's the other one? Oh, don't judge me. Don't judge me. But see, I'm trying to, if they come together like this, and I'm trying to make NO2 and Cl, if I want to make Cl2 here, these guys, that's not going to work. Those two chlorines, it doesn't have the correct orientation for those to come together to make chlorine gas. But if it collides in this manner, and the chlorines kind of come together, you can make chlorine gas and then two NO2s. So that's pretty cool, right? So, like with the Velcro, it has to have the correct collision orientation. And this is actually one of the release exam questions that you'll do here in a minute when I get done talking. It's on that paper you already have. So, there's your one. Activation energy. This is why I chose to do thermite with you guys yesterday. And there's a pretty high activation energy involved with thermite because you have really strong bonds in the rust. But anyway, the kinetic energy from the colliding reactants, it has to be with sufficient force to actually make, this thing is called the activated complex. It's where they're stuck together for a second before they break apart. You have to have enough energy to make this activated complex and then to have them go in their own way. So like this would be my aluminum oxide and my iron. For the aluminum and the rust to come together with enough force for it to separate, you have to get over the activation energy. Notice that this is actually, this is an exothermic reaction. You release energy in the process. This is the energy you started with. You had less when you ended, so energy was released. See that? You okay? Piece of cake. So if the energy of the collisions, if it's less than the activation energy, then you're not going to make any products. So let me show you what that looks like. These marbles, though. So if you just right? Nothing's going to happen. You see? Some Velcro. But nothing happens. So if we go like this, they're definitely going to be stuck, right? So you have to have enough energy in the collision to make that, like I said, that temporary where they're stuck together. Like I said, it's called the activated complex. So to make that, To make that intermediate, you may know that word a little bit better, you need enough energy in the collision. So if there's not enough energy in the collision, then you're just going to keep having reactants. So you're not going to make products. So if they come together but not with enough force, they're going to separate back out. Did you see that? I'll show you again. If they come together but not with enough force, then they'll just separate back out, and you don't make any products. Whee! This is very analogous. It's always about a ball rolling up a hill. Whatever. Yeah, okay, sure. If you don't push the ball hard enough up the hill, then it's going to roll back down. You have to roll it hard enough for it to go down the other side. That's another way to explain it. So look at that Maxwell-Boltzmann distribution. Remember that guy? Yeah. Okay. So this is where sort of the rubber meets the road on the hill of these reactions. So with Maxwell-Boltzmann distributions, remember as we increase the energy, as we increase the temperature, you increase the average kinetic energy of your particles. And so remember, it flattens out and goes to the right with increased temperature. This is this good stuff that we already learned. If this is the activation energy at increased temperature at this green, let me show you here. I'll highlight it. You have this many. You have that many particles that are going to give you a collision with enough kinetic energy to get over that activation energy. That's at a higher temperature. So that's why at higher temperatures reactions go faster, because not every particle is going to have that higher level of energy, but you're going to have more that do. So if we look at that bottom graph though, at 500 degrees Kelvin, and we look at the fraction that have enough energy to get over the activation energy, it's much lower. And that's why reactions go faster at higher temperatures. Are y'all still okay? So it's like I said, it's like 500 objectives right here. So anyway, higher temperatures, more colliding with enough energy. So the activation energy for unimolecular decomposition reactions. Okay, so, do you guys remember chlorine? I hope, if you didn't take, all the non-AP environmental kids just looked at me crazy. So here's the thing. Ozone is in the ozone layer, and it keeps you from getting skin cancer. That's the most basic thing I can tell you. But this is ozone. O3 is ozone. And if you add in something like chlorine is most common. You can do stuff like bromine or fluorine, any of the halogens. But what you got, this little M guy is standing for like a catalyst, like chlorine, and it'll break down ozone. And I've seen this reaction that they have like 3 favorite reactions. One is that silver chloride one, where it's like silver nitrate, and then silver chloride makes precipitate. They use that one over and over again, and they'll use ozone over and over again. But this M just stands for a little catalyst, and we're going to get to this catalyst here in a second. That's going to break down the ozone. So the energy required to break down the bonds and the reactants is obtained during the collision with a solvent particle, and I'm going to go with chlorine because most of y'all know what I'm talking about. For this reason, unimolecular decomposition rates increase as temperature increases. Well, the temperature increases, the rate increases. Fine, because this is going to collide more. That whole slide, well, just repeat what I just said. That's it. Are you still okay? Just nothing. I didn't add anything new. 0 things new. And see, chlorine comes out the end, and he goes and gets another child and kidnaps it. Remember? Sorry. If y'all what? But this is chlorine. Oh, Olivia's one of the triplets.
When he kidnapped Olivia.
Yeah, no, he's right here with Olivia. Okay, I'm going to show you the whole process, and I'll show you the one in the basement and everything. That's not the end of the PowerPoint. Do you remember Olivia ran away? This is a multi-step reaction. We're going to get to that. So if you're wondering what exactly happened, it's in there. It's just not in the overall reaction. I got you.
Other elements.
No. It's this multi-step. I got it. We're going back to this. So this is super difficult. Are you ready? This is gonna blow your mind. The higher the activation energy, like the steeper that hill is, it's gonna make that reaction go slower.
Whoa!
It's crazy talk. I know it. I'm for real. So If you have a higher activation energy, you're going to have a slower rate. You think you probably remember that? Yeah.
I don't know.
It's tough. Generally, if less energy is required to get over the little hump here, more reactants will collide with enough energy. And if we go back to that Maxwell-Boltzmann distribution, I can show you that. I actually am going to show you that because that's what they like, right? They like this little graph. This is like their favorite picture. They have it in their family album at the College Board. So if here's my activation energy, if the activation energy is right here, excuse me, look at all those particles that have enough energy to make the activated complex. See, a bunch more. If you lower the activation energy, more particles have enough energy to make products. Y'all still cool?
Yep.
All right, let's keep going. This is, like I said, pretty straightforward. In summary, yeah, okay. I kind of accidentally spoiled the fun with this one. If you look at your energy when you come in versus your energy when you come out, if you have less energy at the end, it's exothermic. This seems real easy. It's because I'm doing this thing where I smile at you and I say it out loud. It makes you feel good, but you might want to make sure you got that on your own. Look at the energy coming in. If energy is released, because there's less at the end, then it's exothermic. Some energy was let out of that. Because the energy at the end is lower than the energy at the beginning. They're going to show you, this is a very common question, they're going to show you this energy profile, and you have to look at the beginning and at the end and tell if it's exothermic or endothermic. They're not going to give you an enthalpy value. I mean, sometimes they do. But look right here. I have this much energy coming into the reaction, and then I have this much energy coming out. I have more at the end. Energy had to come in, endothermic, okay? And that change in energy is the energy lost or gained in a reaction. Lost or gained. I didn't make this, but there is a typo. So, if we're looking at bond energy, which that's something that happens too, this is also relevant for the potential energy in the bonds. But if you just think about it, like I said, you look at the energy when you came in and when you come out, it's less than energy left, you know. So, y'all okay with that? All right. So we had done this when we had talked about the enthalpy of reactions. And do you remember on Hess's law, if we reversed a reaction, we had to reverse the sign of the enthalpy? Like if it was a negative one way, if you reverse it, it was positive the other way? Well, look at here. If I do this forward reaction, see, I'm going this way, okay? AB plus C equals A plus BC. If I go forward, I can tell I have less energy when I left. This is exothermic. Yeah? Well, if I do the forward reaction, it's endothermic. So that just goes back to something we already learned, and that's why. Okay? You okay there? All right. So notice the activation energy for the forward reaction is actually less than the activation energy for the backward reaction. So that actually gets reversed too. It's just like a hill and a bicycle and all that stuff, but I don't think that's as helpful as just looking at the energy changes. Kinetic control, this is like Rust. We haven't gotten to free energy yet, but like I said, kinetically favored and thermodynamically favored aren't the same thing. I'm going to save that for chapter 16. Okay, great. Doesn't matter. It's not on your test. You're fine. You're okay. We'll definitely cross that bridge. The Arrhenius equation. The thing about the Arrhenius equation, there is an exclusion statement in the learning objectives that says I don't have to teach it to you. Like I'm sure. But Clint, when Clint went to visit Tech, what were they doing in their chemistry class, Clint? Okay. Right. So I know this is something that's on the chemistry Olympiad thing. I don't know. I don't find it of any value. Let me tell you how this works. The College Board wants you to understand that if you lower the activation energy, the reaction rate goes up. And if you raise the temperature, the reaction rate goes up. I can do that all by myself without this reaction. But if I'm just going to scroll through these next couple slides. If you know that you're not probably going to be in like the chemistry Olympiad, or you're not really probably going to be a scientist, or you're pretty much like struggling to pass this class right now, just stop listening to me for a minute. If you're good at math and you want to hang with me while I go through this, then I'm not going to stop and work my pen. I'm just going to show you what they're doing. But you totally can just be like, la, 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 and that's fine. But I think it's of value for me to at least show it to you. This is good, solid chemistry. Like all the chemistry nerds of the world that teach AP chemistry, they got super pissed when they threw this out because this is like the heart and soul of chemistry. So anyway, that whole rate constant, remember that guy? Stop listening to me if you don't. If you're just like, I'm just barely hanging on. Just stop listening to me. Work on something else. The rate constant is equal to that little active. Wait, that A. Yeah, that's the frequency. You know the whole E thing. That's just like that E from math. You know, like the natural log of E is 1. That's that guy. This A is a new thing. This guy, that is your activation energy, and that is R. Do you remember the ideal gas stuff? Do you remember that R? Does that number look vaguely familiar to you? That's that R. And then the temperature. So the only thing that's new, like I said, is that capital A. It's the constant related to how frequently the stuff's colliding. That's changes. Now, what just happened? Let me show you what actually happened here. It might be better if they just make magically think. I may have to use my pen. Are you okay if I use my pen? Okay. Let me find this. Because they skipped about 3 steps and I don't really like that. If I screw this up, don't judge me. If you want to judge me and be sad that I messed up, good luck with the rest of the class all by yourself. Anyway, okay, so let's write down their original one. K is equal to A, and then E to the power of the negative activation energy divided by the gas constant and times the temperature. So, yeah. These are the things they're going to have a value for. You can't do anything with this stuff up in the exponent. So the way you get stuff down when you have this base here that's an E, the way you get the things down is you use the natural log. So the natural log of K is equal to the natural log of A. Now, this is where you should stop listening to me if you don't like math. When we have, like, just the identity of, is it identities? Like, logarithmic identities? When things are multiplied, they're actually added. Yes. Y'all know that, do you? Yeah. Okay, good. So anyway, this little guy plus the natural log of E, I'm going to take the natural log, that's going to bring all that down, and that's going to be multiplied. That ends up being 1, right? It doesn't matter if you don't understand, because it's not on the test, but, whee! How does that make you feel? That went away. Gone. Is that okay? Okay, cool. So that gives me the natural log of K is equal to the natural log of A plus negative. And what they've done on your sheet is they've taken and broken this fraction up. When I was taking these tests in summer, I was like, oh, that spells the word ear. So works for me. It was fine. I passed my test, you know, whatever. And then times 1 over T. That's how they did that. I'm gonna go back to that slide that had this moved around. I think what they had done was they're using it to find the slope of the line, but that's what they did before they did all that other stuff. Let me not clear that in case I need it. So all they did is they just moved it around. And I think they just, honest to God, just swapped those two. Did they just swap these two? Yeah. So whatever. This is the slope of the line. This is your x value. That's your y intercept, and that's your y value. Okay, so whatever. The thing is, this stuff is going to be plotted as a line. And if you graphically show this line, and you know the slope of the line, this is a constant, so you can divide the slope of the line by this constant, and you can get the activation energy. What happened? Calculus?
Yes, that's a second.
Great. Okay. Oh, oops.
Yeah, that's what that is.
So anyway, do y'all remember from like math class where you go to find the slope of a line and you got like y2 minus y1 over x2 minus x1? Well, there's your 2 points. You can do that whole algebra thing and find the slope of the line. Whatever. Those are just points on that line. There's your slope. And since the activation energy divided by the universal gas constant, see, that these just doesn't sound good when I say it out loud. I don't like it. If you take the slope, though, and you divide it by r, because that's the slope, then you get the activation energy. It's just like that. We don't have to do this, but I just thought I'd show you just for fun. Are you having fun?
Yeah. So why do they have that way of finding K versus like the way we were finding K or what concentration? Is it because that has more variables in it?
It's because in this situation it gets a little bit more specific and you can take into account that capital A value for the frequency of collisions. For example, if you have something that is termolecular and 3 things have to come together, that A value is going to be a little bit less, and so you can take into account more things. But I'm out. Moving on to stuff that we have to know. Talking about that chlorine thing, chlorine and all the kidnapping, that thing. Or just any reaction if you don't know what I'm talking about. Most reactions do not happen in a single step, okay? So there's this thing called reaction mechanisms. And at the end of class, I'm going to put up another giant sticky note, and this is the 4th way to find the reaction rate, or the rate law for it, okay? So the steps that happen are called elementary steps. And so this reaction where you take nitrogen monoxide and oxygen gas and you get nitrogen dioxide, it actually happens like this. The first step is 2 NOs form N2O2, and then the N2O2 combines with oxygen and gives you 2 NO2. Do y'all remember where we played the memory game, and if it was on this side and that side you could take it out? That was a good investment over time, because you can see that this guy and this guy, they're on both sides, and so those cancel out, and then these elementary steps have to cancel to give you the overall reaction. You see that, how they cancel to give you the overall reaction? But it's 2 separate steps, and there are a series of steps that sum to the overall reaction. Are y'all okay with that? Feeling comfortable? 2 elementary steps. Cool. An intermediate. If you are of intermediate level, y'all have the intermediate man here? Is that a thing? Kind of like
Awesome.
call something different. Well, if you're playing a game and then there's like beginner, intermediate, and advanced, intermediate's in the middle, okay? It's not they're going to ask you questions, you know, is this an intermediate or is this a catalyst? And you have to know the difference. An intermediate pops up in the middle and it goes away in the middle. It ain't at the beginning and it ain't at the end, okay? So you can tell how this is just up in the middle here. So it's an intermediate, okay? Are you feeling okay about that? So this N2O2 is a reaction intermediate. It's not the beginning, it's not the end, just kind of pops up in the middle there for you. Let me show you this with marbles. If I didn't have like, thank you children in, are these too smooth there? Thank you children in China, I appreciate that for making this with me. So 2 NOs, this is an NO, and this is an NO, see it? So I was kind of telling y'all when they collide, it's called the, I used the word about 5 times a minute ago, the activated complex. This N2O2, there it is, you see it? N2O2, you see it? So this is something that where they're stuck together for a second before they break up and make the new thing. And what do we actually end up making over here? 2 NO2s. I don't have enough marbles, but like some of y'all have gotten it to make a 3 thing. I can't do that with actually using my hands, but you know, then you'd have another one over here. So that's the thing. It's kind of like this activated complex, that temporary thing where they collide, they haven't broken up yet. Okay? Does that make you feel all right about that? Okay. So N2O2 is a reaction intermediate. Intermediates are just in the middle. They're not the beginning, not at the end. Okay? And they're going to cancel out. So when you take your pencil and you mark out stuff that matches like you're playing the memory game, with the crap that you mark out, that's the reaction intermediate. So determining the rate law. I made a big point about this the other day, and I'm still sure, and I'm still right, and this is a thing. You cannot look at the overall bounce equation and tell the rate law. Like the one where stuff's been canceled out and there's only one step, you can't look at that and tell the rate law. But if I told you on this one, the rate law was NO2, and then the NO2 was second order, and this is the rate law, I mean, I can tell that this is zero order, but I just gave you the rate law. This ain't one step. So let's go ahead and look at the steps that do this, and we'll kind of understand this a little bit better. Are y'all with me that if you have that one step reaction, and you don't have any other information, you cannot determine the rate law? Are you okay with that? If you have the elementary steps, though, you can determine the rate law from the elementary steps. So somebody emailed me over the weekend, and they said, you know, how do I know if it's going to be, if this is the fast step or the slow step or whatever? They're going to tell you that, so that's not something that you're going to have to figure out. So anyway, the rate law for the elementary steps. Notice that this first step just happens to have this 2 here and this 2 here. Now, in this first step, the rate law for this elementary step is the same as the rate law for the overall reaction. I just showed you that. There it was. These are the same. And there's a reason for that. So, in this situation where you have the elementary steps, you can actually use the coefficients as your exponents. Let me show you why. What they're going to do is they're going to give you the elementary steps, the reactions for them, and they're going to tell you which one's slow and which one's fast. Now, if I'm on an assembly line and the guy beside me is like taking a really long time and I'm going pretty fast and we're making like, I don't know, we're elves making little toy trucks, okay? The guy beside me is putting the wheels on, taking like way too long, and I've just got to put the bell on at the end. Like the guy making the wheels and putting the wheels on, that's going to be the slow step. He's going to determine how many little toy trucks I can make, okay? So the slow step, when you have all these elementary steps, when they tell you, hey, this one's a slow step, that's going to be what's called the rate determining step. I don't think that's up there. I don't know if it's in this PowerPoint, but that's a thing, so we better ought to write it down. Sometimes it'll be called the RDS. RDS, rate determining step. Okay, so your slow step is going to be your rate determining step. So this is your guy putting the wheels on the little toy truck, and you just got to put the bell on at the end. You're waiting for him. As soon as he gets done putting the wheels on, you're ready to go. Now the overall rate law for this sucker is the NO2. And this carbon dioxide was zero order. Here's the thing. You can go as fast as you want, have as many bells ready as you want. But you getting a whole truckload of bells, that ain't going to make this go any faster. So the reason the carbon monoxide is zero order, the concentration of carbon monoxide ain't going to ever speed this up because you're waiting on this to get made. Okay, so that's why things are like first order, second order, zero order. I don't know if that's on the AP exam, but that's kind of cool, right? That's neat. So the rate of the overall reaction is always equal to the rate of the slowest elementary step. Yes, sir?
Is the second reactant always going to be in step 2?
No, the slow stuff is sometimes in the step 2, and that makes it a little bit more difficult. But I gotcha. I'm actually going to blot out the crap that they wrote on this and make that easier. That's fine. Y'all are kind of getting a little tired, and so why don't we just take us a minute. Don't listen. Just stop listening to me. I think if we were just going to stop there for just a second and take a little load off. I'm sorry. We're almost done, sort of. It's easy though. So if we have a slow initial step, the rate law for the overall reaction is equal to the rate law for this first step. I just showed you that. So the rate law for this is going to be NO2 And the reaction order for this is going to be second order. Okay? Y'all, we're good with that, right? Now, if the second step is the slow step, a little bit different. It's still gonna proceed at the rate of the slow step, but the problem is that the NO3, the rate law, y'all. We did the rate law. Do you remember how we took? We had the reactants and put them in little brackets, and we put like exponent on it. NO3 is in the reactants for the second step. Is NO3 in this? No, so I can't put a rate law with something that ain't even in the chemical equation. That ain't right. We can't do that. So what we're going to do instead, and this is where I'm going to get my marker out and turn it white. I really am super duper going to do that. Yeah, that'll work. I'm going to white out what they wrote. And you'll see why. I don't know if you're actually able to do that, but if you can't, yeah. So, okay. Don't worry. No. Come back. It's fine. Everything's cool. I need to make this a little bit bigger. That answer. Oh, that's actually that. Did you see that? They were totally misselling this to me. That's the answer. That was still smaller than a loop. See, la 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 la. This is all this stuff written on your paper?
Yeah.
Should totally make that go away. I didn't have any problems.
I wonder why.
This is actually super duper easy. Okay, ready? Just be like, nope. Yeah, just mark that out. This. It's going to take about 10 seconds to explain this to you. All right. Yeah, you ready? All right. So look at here. This is my reaction intermediate. Okay. I wish real paper worked like this, though. You know, that would be cool. So this is my reaction intermediate. Where did the stuff in the reaction intermediate, where did it come from? What did I need to make that? Cool. Okay? So the second step is the rate determining step, right? My RDS is right here. What I would like to write down, but I can't, I'm not allowed to. What I would like to write down is this. Can't do that though, can I? Can I do that? No. So what I'm going to do is super difficult. I'm just going to substitute these two guys in there for that. Okay? So let's just, no, can't do that. Check your equation. If the stuff in your rate law is not in your equation, then it's not okay. So what I'm going to do is I'm just going to throw down an NO. Do you see how I have an NO right here? How many NOs do I have?
Oh.
You cool with that?
Yeah.
I can write them down twice and then, you know, show my work if I need to.
See. So second.
But then I also, I got this guy too. So my overall rate law for this, oh no. I take peekaboo with that mess. I don't want to do that. I'm going to write it right.
That's your white pen.
Yeah, oh, okay. Oh, yeah. You guys are so smart. Oh, my gosh. Yeah. That's good. My overall rate law, though, is just going to be the rate. I don't like this game anymore. The rate is equal to, is always going to be equal to K.
Oh my god.
It'll go away in a second.
I think that's the mail, Miss Raymond.
The rate is equal to K. I ran out of room. Do you mind if I just write it up here? The rate is equal to K. And then, look, don't freak out. I have 1, 2 NOs. Okay, and then I have an oxygen. And that's it. Yeah, that's really it.
But that's because
I was looking at this and I was like, that's not how to do that. And I spent time like looking it up to make sure I was right, and it's fine. I'm sure. No, I really spent time.
because I was like,
No, and I'll show you that's the answer they got. Watch. See? NO2, O2. That's,
why does it say K3?
oh, it's the rate law for that.
Yeah.
Or the rate constant. That doesn't mean anything.
Alright.
It doesn't mean anything, dude. You put a K, okay?
Alright.
It's fine. This is,
Yeah, I was like really confused.
the reason it has a 3 down there is because this intermediate step has a rate constant and this first step has a rate constant, and this is a different rate constant. But it doesn't matter. You're fine. Chemists are going to determine the rate law through experimentation. The rate law tells them what the slowest step is, and then they go and do experiments. This giant chart is very overwhelming. It's really not, though. You don't even need this chart. I mean, because that last reaction we had NO2, and it was to the second order, and then oxygen. What's the overall? What was the overall order of that reaction? Okay, so. Okay, if I just have one of the reactants in my elementary step, that's the rate determining step, it's first order. If I have 2 of them, and this is a 2 at second order, if I have 2 different things, also second order, this is what we just did, and it's just a big scary chart for no reason. You don't need this chart. That just is not helping. Okay, so do you remember from yesterday, same stuff as yesterday, the rate is equal to the rate constant times the concentration, and the higher the K, the faster the rate. Okay. Standard conditions means everything's 1 molar and at 25 degrees. So this is 10 to the -4th, this is 10 to the -6th. Which process is going to have, which one's going to have a higher rate? The first one, because the rate constant's higher. Bigger number times same number gets you a bigger number. Okay, so that's easy. Here's another one. Now this one's easy, but you have to think about it. So think about your marbles. You got 2 of these marbles and 1 of these marbles, and this marble and this marble. Which step in these 2 are going to be faster? You want to think about it for a second? Think about it. I'll pick somebody. Oh, people are like, don't pick me, don't pick me. Avery? Which one is going to be faster? What? Fair enough. Pick somebody that, who do you think was paying attention? Drew, which one do you think is going to be faster?
Maybe I can guess myself. I want to say 2 because it would be a smaller number if it's not squared.
Okay, here's the thing. What this means in process 1 for my elementary step, I have an A plus a B that has to come together in my elementary step. So I have 3 different marbles having to come together and hit each other just right. Versus this marble and this marble. What's more statistically probable? That's all there is to that. So that first one needs a collision of 3 particles. That second one only needs 2 different ones. This stuff really ain't that bad. I just want y'all to know what you get me for Christmas.
What do you want?
I don't know.
Science stuff. I'm against.
I tell you what, for Christmas, I don't want to have to teach y'all no more. I'm having such a good time, but this has been hard, and it's hard for y'all too. And in the future, it won't be so bad. Okay, so we're to the easy part. It's to the time we got a cartoon and we got shoes, and it's fine. Okay? Yay! Oh, I guess I should tell you what a catalyst is. I love it. I have a story. I got it. It came to me when I was driving my car. But a catalyst is going to increase the rate of a chemical reaction by participating in the formation of a new intermediate, providing a mechanism with a lower activation energy. It basically gives a faster way for a reaction to happen because you go about it a little bit quicker, and I'll have some examples for that. Catalysts are not produced or consumed in the reaction. They're there before the reaction starts, and they return when the reaction is complete. So here's the thing. If you want to go on a road trip, right? Let's say I wanted to go from here. Where would be a fun place to take a trip? Anywhere except school. Cool. Yeah, okay. So, I gave you a funny look. Alright, let's take a road trip to California. It would be super fun.
Yeah.
Yeah, we're going to get on the road, and we're going to walk there. So we can totally make there faster. It's there when you start, and it's there when you end, and it just helps you get there faster. It doesn't participate in the reaction. Does it get out and look at the Grand Canyon? No, it doesn't. It totally doesn't get out to check out the world's biggest ball of yarn. But it's there when you start, and it's there when you end, and it gets you there faster. Is it good? It's good. Is it good?
Teacher of the year.
Yay!
Okay.
Okay, so if we look at what that actually looks like in a reaction, watch, here we go. And I love it, and this is just, chlorine has Cadillac, okay? And so he's there when you start, he helps stuff go a little bit faster, and he comes right back out at the end. See, where's my little car?
You still have it.
And then he's done. Doesn't participate. It's a monster truck. It's totally fine. I should, for fun, print out a Cadillac symbol and tape it to the top of that. And that'd be like the little crown thing. I don't really know what it is. It's like and it makes okay. So here's how actually chlorine destroys the ozone layer. So I can really understand it now. So chlorine comes in and it does still an oxygen. There it is. There's Olivia and there's the twins. Sorry, y'all. If you haven't, I'm sorry if you don't know what I'm talking about. Just say the names of the elements. And then remember there was that other oxygen in the basement. Do you remember that?
What? I can't handle it when it says it right there in red, like at the end.
Back to reaction.
Oh, and by the way, when I was good, because I'm second guessing myself, because I'm like, this guy that made this must be smarter than me, because I paid him a lot of money. But it's definitely 100,000 ozone molecules, because I looked it up. So I know about that. So it's not 100, it's 100,000, and I'm sure because I fact checked it. So this is wrong. No. But anyway, you can see that the other oxygen binds with the oxygen that the chlorine has stolen, and then you get O2, and then the chlorine can start the process over again, hundreds of thousands of times. And look, this reaction intermediate, that guy goes away, cancels, right? So this is your reaction intermediate, your CLO, and your catalyst is there when you start and you end your road trip. So can you tell the difference between a catalyst and a reaction intermediate? Because they're going to ask you that.
Yeah, no.
You good? This is the overall reaction. The chlorine isn't in the reaction either. This is really what happened. This is the breakdown of ozone, right? But the chlorine makes our intermediate there. What? Not yet. We're just on water now. So basically, without a catalyst, this is the reaction. The activation energy for this first reaction. The activation for this first reaction is taller. But if we go and make this intermediate, the CLO, the activation energy needed to make that intermediate is less. So you end up doing the same process, but this intermediate is less energetically, yes ma'am? Why is it less? We probably have to look at the bond energies and stuff. Yeah. It's determined experimentally. That's a great cop-out, isn't it? Anyway, as far as equilibrium goes, you don't know about this yet, so we're not worried about that. We'll definitely come back. There's different kinds of catalysts, acid-base, surface, and enzyme. I'll do the acid-base one first. This R group, this R thing, these are just like CH3. They're like a carbon and 3 hydrogens off the side, and this one with a little apostrophe might be like a little ring. It don't matter. What ends up happening... Stop reading that. It's freaking you out. What ends up happening with this is you take, where is it at? Maybe I have to hit it one more time. Oh, there it is. It's right here. Let me zoom in so you can see a little bit better. What ends up happening with this little carbon right here? It becomes a little bit positive, and so when it bonds with the water, where is the water? There it is. It's just easier for it to bond with the water because it's a little bit positive. Not that big of a deal. So it just makes that happen a little faster. The two that you really need to know a little bit more about, the first one is a surface catalyst. So excited. You ready? All right, take your shoes off. You don't have to, if you don't want to take your shoes off, you can borrow my shoes. They're really good. Do you want, I really want you to do this. I'm going to show you how to do things. Don't question me. Just one shoe's fine. I'm taking off two in case you need to borrow one. My shoes are pretty clean and I'm not that super gross, so. You gotta work with a partner. And your partner is gonna hold one shoestring and put the air like this, and then you're gonna tie the shoe. The only thing you can touch is the shoestrings. Well, okay, yeah, that's where I'm getting at. Go ahead, tie the shoe. You gotta work with a partner. Here, I got another shoe. I'll work with these. Oh, no, you can work with each other. Tie the shoe. You can only touch the shoestring.
Can I touch the shoestring? Only use 2 hands.
You can use 2 hands, but you can only touch. Is this too easy? It should be hard. Is it too easy? Should we do it like this?
We only use 1 hand. You use both hands.
Ah!
Oh, crap.
Is this easy?
Yeah, I'll do it.
I want it to be harder.
I'll do it.
Would this be harder? Alright, good. Let's just do this one. Yeah, good. That looks like a hot mess. That looks great. Boom! Get it!
I would have had it.
Okay, what's that?
Ours is prettier.
The shoe has to be hanging in midair. Y'all are so cheap. The shoe has to be hanging.
So I do it, but then untie itself because it's holding it.
Yeah, it needs to be hanging. You can't be holding it up. Try again. Start over. Y'all cheated. Oh, I know I didn't cheat, but y'all struggled. Y'all had to struggle. The struggle was real right there. Y'all good. This should not be easy.
I can go back and part again.
Yeah, it wasn't.
Did it right?
It wasn't easy.
It was easy when she did.
Okay, yeah.
What's your favorite?
Dave just screaming had it. Yeah, wait for the cross.
My socks are actually gorgeous.
We did do it. We did do it.
Did you get it?
This little had my shoe covered.
I'll give you another minute. Some reactions take longer than others.
That SpongeBob song.
Which one?
Where he learns to tie his shoes to
This is like
like I could get that.
I don't know why I thought about shoes when I learned this, but I sure did. So if I'm taking some nitrogen gas and some hydrogen gas and I'm trying to make ammonia, and those are gases just, go with me now, are you looking? Those are gases just floating around in the air, and then I'm going to try to like do a reaction between them. That kind of makes it hard. But a surface catalyst, this is really deep, a surface catalyst actually will absorb the gas, which just means it sits on the surface of the metal, and then the reaction takes place faster.
When did you think of that?
I don't know. This is what I know. This is what I know to be true. Somebody more omniscient and more omnipotent than me won't try to pass AP chemistry because I'm not that smart. But that's how. So do a surface catalyst for me. Just do that. Do it. Do it. Do it.
I did it.
I'll do it right now.
Oh yeah.
Yeah, so put your foot up on top and tie your shoe.
Do it better. I literally don't.
I guess I can put my shoes back on. No, actually, we're not quite. No, we're done. We're done here. I got a movie for the other one.
He plays for the Wizards. This is true. J.
Alright, everybody got their shoes back on? Cool. Working on it.
Oh, shit. Yeah. Wall.
All right, so let's see that in real action here. A surface catalyst takes reactants in the gas phase. And so, like I said, these things are floating around in the air, just like your shoe is floating around in the air. And the gases, watch them, I think this says a little cartoon for you. The gases get adsorbed, which just means they get stuck to the surface. And then they are easier to react with each other. And the reaction would be like you tying your shoestring. So atoms move around on the surface of the metal. They're kind of stuck to it. And they migrate until they make the new product. That's a surface catalyst. How does that make you feel? Pretty easy. And then they can then go about their little ways and make the new products. This is how you make ammonia for fertilizer. Enzymes as catalysts. I have a little movie for this. Here's the picture. It's a much better if you watch it in like a actual motion. So I got that ready for you. Let me go to that part of it. Oh, that green thing.
1. Each enzyme has an active site. This is the groove in the enzyme where the molecules they act on, called substrates, are captured and made to undergo a reaction. The substrates are either broken apart or combined together to form products. For instance, starch found in the bread that you eat is digested to form simple sugars called glucose that is then absorbed into the body. Glucose is used up as energy, but when there's too much of it, special enzymes combine the glucose molecules together to form a giant molecule called glycogen, which is then stored away in the liver and muscles for later use. Number 2, enzymes are very specific. Each enzyme can only bind to one type of substrate. Let's look at the case of lipase enzyme, which breaks down fats. Molecules like glucose and proteins cannot fit into the active site of lipase. Only fat cells can bind to the active site because they have the right shape. This ability to act on just fat cells is very important for lipase. Lipase converts fats into energy. Now imagine what would happen if lipase can also convert proteins into neurochemicals for the brain to function well. If you no longer need the extra energy from your storage of fats, lipase will be deactivated. But this means that lipase can no longer produce precious neurochemicals for your brain. In other words, when you start burning fats,
that's AP biology. Did you see the part where it has the substrate and it fits in there and it either gets broken apart or comes together? So it's kind of like it's sort of like instead of putting your shoe on the table, you're holding the shoe and you're tying it. But basically, it creates a space to hold something that's floating around still so that the reaction can take place a little bit faster. Anyway, so yeah, if you were tying it in space, you'd have to hold on to it. That works. So there's that. What I want you guys to do, hey, I'm done talking, and I'm not going to talk tomorrow either. It's going to be great. So what I want you guys to do